this next lesson, we're going to continue talking about hybridization, specifically about multiple bond hybridization. So let's start. Okay, before we do that, let's just review a little bit of hybridization in an H2O molecule. So the question here is asking to describe hybridization around oxygen in H2O. All right, so let's draw this quickly. Okay, so oxygen we know to be, right, just reviewing VSEPR here, we know to be a bent shape with two unbonded lone pairs, followed by two hydrogen molecules or two hydrogen atoms like that at these approximate angles, right? So we have to see that oxygen requires a lone pair here, and then a half-filled suborbitals here and a half-filled suborbitals here. So we take its orbital diagram, its ground state orbital diagram, oxygen's, and we see that it has 1, 2 electrons in the s orbital, 1, 2, 3, 4 electrons in the p orbital with one of them paired up as a ground state. And going back to that water molecule, that VSEPR shape, we need two half-filled suborbitals. Look, we have one, we have two, and we also need two complete electrons, two pairs of electrons, lone pairs around the oxygen atoms, and it turns out we have that. So our excited state is actually going to look just the same. Right, now our hybridized state, all this does is to prepare for bonding, it will just take all of these suborbitals and they would all mesh or come into a hybridized between 2s and 2p state, which would just mean because we have one s orbital, right? So we have one s orbital. Because we have 1, 2, 3 p orbitals, it'll look like this, sp3. 3 again corresponds to the number of p suborbitals, the s to the number of s suborbitals, and we have an sp3 hybridization around oxygen. All right, so that's just reviewing hybridization around an oxygen atom in a water molecule. Okay, so far we've seen single bonds. Examples that we looked at were hydrogen, various other, we especially spent some time on methane, right? And we saw how bonding occurs in sp, sp2, sp3 hybridization states. We also went into sp3d, sp3d2, right? Now, they involve lone pairs certainly, like we just saw in oxygen in the last example, and single bonds. Now, what's different here is that we're going to move on to multiple bonds, so double and triple bonds. But again, these lone pairs, last time we talked about these p orbitals. We'll talk about these p orbitals and s, but an orbital looks like this, right? For them, for a half-filled electron, let's say one spin up here, one spin down, when they collide, this head-on collision produces what's called a sigma bond or a single bond. Now this can happen between two s's, it can happen between s and a p, right? And after they've hybridized, you have an sp to the whatever number of p's that is. So these are the hybridized states colliding, right? So this happens as a direct overlap, right? Direct head-on collision. These single bonds are called sigma bonds. Pi bonds, on the other hand, when you have double or triple bonds. So double or triple bonds only, right? We'll have a pi bond. Right, now what happens here, and this shows you, this picture shows you the difference between a sigma and a pi bond. A sigma bond, like we saw, they will, after they've hybridized, of course, so here for your p's especially, for your sps, they will collide, head-on collide, right? They'll create a sigma bond. Now your pi bonds, they don't head-on collide. They instead overlap. And they overlap in the same dimensions. So let's say this is a PZ, right? This PZ is going to overlap, and that will create a double bond, right? A double bond has one pi bond. A triple bond has two pi bonds. We'll get to those details in a bit. Okay, now as they begin to overlap, see how these regions here are overlapping, right? Electrons now, they will create what we know now to be called these regions where there are no electrons or unlikely to have electrons here, or in other words, nodes. A 2p orbitals that are unhybridized that will form those double or triple bonds will create this funny looking kidney bean shape. Now this looks like two separate bonds, but in reality this whole thing here is just one pi bond, right? Just one pi bond. 2p orbitals in the same spatial orientation, in the same spatial dimension, overlapping, creating this pi bond. All right, now let's look in more detail at an example. So this is, if you remember from your organic chemistry unit, 2 electrons would normally be ethane, but because it has a double bond, it's ethene, right? A good example to begin, talking about partial hybridization. We'll see why it's called that. They will form sp3 orbitals. We'll look into that right now. All right, so let's move this up for now. Okay, so here is your ground state for carbon. We've seen that has 1, 2, 3, 4 electrons. Your 2s is completely full. Now here we have 1, 2 suborbitals that are half filled, and that means we can then pair up or create a bond to create 2 bonds, one here and one there. But we don't need 2 bonds. We need 1, 2, and here's where that double bond is. Now double bonds are made up of 1 pi, right, and 1 sigma. Pi bonds are made up of unhybridized p orbitals. So one of these will not be hybridized. The other 2 here will be hybridized together with S, and we'll see how that looks. Let's go back. We need 1, 2, 3. 3 half-filled suborbitals so that you can create those 3 sigma bonds. We're going to move this electron here in its excited state. I'll move it back for now in the ground state, but we're going to have, let's see if I can move this over. Here we go. So 1 electron here. Now the electron that was here, that's going to be promoted, and we'll promote that in just a bit, but I'm going to fill these in. So 1 there, another one for 2py, and then that electron here, this electron there is going to move over here in the up direction, or spin up direction, and it looks like this. Okay, so now we have our 3 required half-filled suborbitals to create the 3 sigma bonds. That's here, here, and here. Now the 2pz, that is going to remain unhybridized to look like this. And finally, one here. Right, so these are these electrons, 1, 2, 3 electrons. Now this one last one appears exactly as it did up here. So here we have 1s, 1, 2, 2p's, that gives us an sp2 hybridization for these 3 half-filled suborbitals that will end up creating those sigma bonds, and then a 2pz, which is exactly the same as this is. Now, this does not hybridize. It needs to maintain its shape. It needs to maintain its orientation, its z orientation, right? This is would be along the z-axis if I've drawn that without confusing you, so 2pz. Now, going back, the same thing is happening. So I've shown you the partial hybridization on this side, specifically for carbon. Same thing is happening in this side. So will have the same partial hybridization on that side happening for that central carbon. So that the 2pz unhybridized state for this carbon will directly overlap spatially with the 2pz unhybridized electron for this carbon. So we get 2 unhybridized p orbitals in the same orientation, right? Both in the second energy level and 2, so 2pz, 2pz, these then will overlap to create that double bond, or to help to create that double bond, while you have these 3 sigma bonds. Right, just another picture here. You see a promotion of that electron to create those 4 suborbitals that were needed. And then we have a hybridization of these 3 suborbitals to give you an sp2 hybridized state, and your unhybridized 2pz orbital looks like this. That creates a funny shape. So in ethene, again, here we have we have a hydrogen s orbital colliding with your sp2. That's 1 sigma. You have another one here, same thing. Your s electron from hydrogen colliding with your hybridized sp2. That's creating another sigma bond. Then you have another sp2 here in this carbon, another sp2 in this carbon. That will create another sigma bond. Then you have your 2pz's. One here, one here. Actually, these are all just one, right? This is one 2pz. All of this here is another 2pz, another 2pz, but each of them do still have that one electron, right? Now they will overlap to create this. This gray or dark gray area here and here, these are actually all just one pi bond. So around ethene we have sigma, sigma, sigma between each carbon, and pi between the 2 carbons to create your double bond. And this is a better picture of how that looks like. Kind of funny. It's something you haven't quite seen in the past. But again, hydrogen carbon, head-on collision here, directly overlapping. Your sp2 hybridized states between both carbons as well, directly overlapping. Whereas here you have that pi bond, right? With these areas here of less electrons, or less likely to have electrons as your nodes, and you have these 2 funny-looking kidney shapes that create actually just one pi bond, just one. Although it does look like 2 separate things, it is just one. Electrons tend to be here and here around a pi bond, or in a pi bond. Okay, something similar happens in the next example in ethine. Here we have a sigma. Right, I'm going to focus on just one carbon for now. So here we have a sigma. Now between these 2 carbons, we also, in the center here, we have a sigma right here, and at the top and bottom we have your pi's. So in this case, you're going to have 2 unhybridized states, 2 unhybridized suborbitals, right? And the 2 sigma bonds that are created are going to be hybridized, and they're going to have an sp hybridized state. Now we'll get into the details. So start at the top. It's ground state for carbon. Looks like this. 4 electrons, 2 of which are in the s orbital. We know we're going to have to promote that electron, right? Because we do need 4 bonds. There are, after all, 1, 2, 3, 4 bonds around the carbon. So we have to promote 1 electron, and we have an excited state that looks like, well, let's just draw it. I don't need these. Let's just draw them. So 1 electron here, 1 here, 1 here. Now this electron got promoted over here, so it's going to look like that. Right, so 1, 2, 3, 4 electrons. We now have 4 unpaired suborbitals ready to create the 4 bonds we need. But now we need 2 sigma bonds, right? One here between hydrogen and carbon, and another one between carbon and carbon. So those are only 2 sigma bonds, and sigma bonds need to hybridize. So here we have one, and here we have another one. So we have an S and a P that will hybridize, whereas these other 2 do not. So here's your S and here's your P to create an SP, and these we just redraw. So 2py and 2pz. We will need 2 unhybridized p orbitals, specifically 2py and 2pz, to create those 2 pi bonds. Right? Remember, the same thing is happening to the other carbon. The other carbon will have the same 2py, 2pz unhybridized suborbitals that will overlap in the same orientations. Right, so the 2pz's will overlap, like we saw in the last example. Right, these regions here will overlap in the 2pz. Now changing the orientation, if you recall our these 3D axes, right? if this is Z, this is X, and if this is Y, then we're going to have in the Y direction, right? These will overlap here, these will overlap here, and this will create a 1 pi bond and another pi bond between the two carbons. Now it will look like this, right? So sigma, remember we have a sigma bond between hydrogen and carbon, a sigma bond between carbon and carbon, um, and that's one central atom. Now the other carbon has the same thing, two sigma, sigma here that we already mentioned, and a sigma there between another hydrogen. So these are all the sigma bonds involved in ethyne. Now here are only the the pi bonds, right? In one orientation we have one pi bond, so these purple lobes here, and in the other blue we have another pi bond. Now put all of your pi's and your sigmas together, and this is what ethyne really looks like. Some people say it looks like a hot dog, right? Sausage in the center, but there you go. That's what ethyne really looks like. Right, another picture over here. Again, we have sigma here, sigma there. Off to the other carbon, we have sigma there. Right, this is between the s electron. This is in the sp hybridized state right here. They head-on collide. Whereas we have 2px, sorry, 2py here, 2pz. They will directly overlap with their corresponding partner electron between each of the central carbons, right, to create our 2 pi bonds. Now, bringing this full circle, benzene circle, what we see then is a more uniform electron density, like we referred to back in day 1 hybridization, right? Instead of seeing higher densities, alternating higher densities in benzene, this begins to explain a more uniform area around that ring. Now, these electrons can be delocalized, and there's more of a resonance structure happening here, but we don't get into those details just yet. Okay, so that is it for day 2 hybridization. Here is your practice. Your textbook's actually pretty good with this, so go ahead and give it a shot and ask questions online. Again, big idea, double bonds need 1 pi bond and 1 sigma. Triple bonds need 2 pi's and 1 sigma, right? These pi bonds can only be formed by using unhybridized p suborbitals. So if you're able to get this at the end, then you're well on your way to understanding this. See you next time.